In class and in the homework, you've been using the power rule to find derivatives of power functions. Power functions, x to the n, and the power rule for derivatives says that the derivative of x to the n is nx to the n minus 1. This is a great formula, it's easy to use, and it works for any n, and you'll use it lots and lots in the next parts of the course. The goal of this video is to try to give some justification for why this is true. Some argument for why this might hold for general n, not just n equals 1 or n equals 2. This isn't a formal proof, it's a sort of informal argument, but maybe it will make this seem a little bit less mysterious. The material I'm covering here isn't required in the sense that you're not going to have to do a derivation or an argument like this. For the rest of the course, the main goal is just to use this. You just need to know how to use the power rule. Nevertheless, I thought it would be good to talk a little bit about where it comes from. So what we want to do is show how the definition of the derivative, this funny limit thing, this is the slope between x and x plus h, how this limit, this difference quotient, eventually gets you to this formula. So I'm going to start with doing an example that we've done before. That's f of x is x squared. So if we want to evaluate this limit, f prime of x is going to be, well, I'm going to plug in for the function, that's x plus h squared minus x squared over h. Oop, and I forgot the limit. Okay, so we're going to have to do some algebra in this and hope that eventually h's appear that will cancel the h down there so we don't have to worry about dividing by 0. And remember that in order to deal with this, we have to FOIL. So I'm going to do this over here. We had to do x plus h times x plus h. This is x plus h squared. And so when we do this, we distribute the x. We're going to get x squared plus xh plus xh plus h squared. So first two terms, outer terms, inner terms, last terms. And a way to think about this is that notice we get 4 terms out of this. So there are two choices as we're expanding this out. As we sort of go through piece by piece, there are two choices. As I do this multiplication, I could either deal with this x or this h. That's 2 choices. I could either deal with this x or that h. That's another 2 choices. So 2 times 2 is 4. There's one choice where I have x and x. There's 2 xh choices. That's why we get 2 of these. And there's only one hh. So if I collect these terms, this is x squared plus 2xh plus h squared. And to foreshadow what's going to come later, I'm going to underline this 2 because that's a number we're going to have to think about a bunch. So I'm underlining this to remind you that this arose because there are 2 ways of getting an x and an h. I could choose these 2 or those 2. Alright, so let's finish this derivation. So this equals limit as h goes to 0 of this whole thing, x squared plus 2xh plus h squared minus x squared over h. And now, as we've seen before, some happy simplification occurs. Still have the limit. X squared minus x squared is 0. That's nice. We've got 2xh plus h squared over h. And now I can cancel h's. So I can get rid of this h and this. So remember, if I divide by h, I have to divide all terms by h, not just one. And that gives me limit h goes to 0, 2x plus h, which is just 2x. So as h gets closer and closer to 0, well, h gets closer and closer to 0, goes away, and we're just left with 2x. So we've done this before, but I wanted to do it again before I did a more complicated thing, just to remind you how this goes, how we can use foiling and the definition of the derivative to come up with a formula for the derivative for x squared. Suppose that instead of x squared, we had something a bit more complicated, like x to the 13. What would happen then? Well, we're going to need to FOIL out x plus h to the 13. So let's think about that. So we've got x plus h, 2 of them, 3 of them, and let's keep going. And then number 12, and number 13. So the picture here is that I've got x plus h times itself 13 times. So we don't just have to FOIL, we have to FOIL, 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 well, and just keep on foiling until we get to the end. So this would be a massive amount of foiling, and it's something we certainly wouldn't want to have to do all the way out. And the good news is that we don't have to do it all the way out. We can realize that we're only going to care about a couple of terms here. So I know I'm going to have an x to the 13th term. And then the next term is going to involve x to the 12th times h. And then I'm going to have x to the 11th times h squared, so on, all the way down to h to the 13th. And there are numbers in front of these terms, and we want to think about what these numbers are. So remember when we did x squared, x plus h times x plus h, there's only one way we could get x squared, by choosing the x1 here and the x1 here. So it's the same story here. There's only one way I can get x to the 13, by choosing the x term here, the x term here, and the x term here. What about the x to the 12th h term? So that, right, notice all of these have a 13th power, in the sense that, like, this is x to the 12th h1, so they're like 13 letters here, there are 13 letters here, 13 letters here. And it's because as we go through, we choose every time either x or h, and we have 13 choices to make. So how many different ways can we get x to the 12th h? Well, this would mean, if we have a term like this, it means that I only chose h once, and all the other times going through in this massive foiling endeavor, I chose the x. So I could choose this as h, and then do h times x times x times x times x all the way. Or I could choose this to be my h term, x times h times x, and so on and so on. Or I could use this to be my h term. So the thing I'm trying to suggest is that there are 13 different choices for which one term I choose to be my h term. So this number here, let's see, let's choose a bright color, is going to be 13. So then there's an h squared term and an h cubed and so on. And I'm not even going to think about what happens over here, because as we'll see, we're not really even going to care about these terms. So let's start thinking about the derivative. So f prime of x, it's the limit as h goes to 0 of x plus h to the 13 minus x to the 13 over h. So I'm going to plug this term in here. Remember, this was x plus h to the 13th. So let me put this big expression in here, and let's see what we get. Okay, so here I've plugged in this expression for x plus h to the 13th, but I've written it in this funny way. So we've got x to the 13, that should be x to the 12, sorry, 13 x to the 12h, and then all of these terms in here have at least an h squared in them. H squared, h cubed, h to the 4th, all the way up to h13. So I'm going to group them all together and just say plus a whole bunch of terms with h squared or higher. So this, between my fingers, is x plus h to the 13, and then we subtract x to the 13. So as before, some cancellation happens. So the x to the 13 minus x to the 13, those terms cancel each other. And now I can cancel an h, like I did before. So h here, h there, those are going to cancel. But remember that we also need to cancel the h here, and so this collection of terms that has h squared or higher now becomes a collection of terms with h or higher. So after I divide through by h, this becomes 11 h to the 1. There'll be an x to the 10, h to the 2, and so on. So let's collect terms and see what this is going to give us. All right. So let's see, this is still the limit as h goes to 0. And I've got a 13. X to the 12 plus terms with h or higher. So any term that has an h or h squared or h cubed, that's going to go to 0 when I evaluate the limit. So terms with h or higher, all of these terms go away, and all I'm left with is this. So 13 x to the 12. So notice that what we've shown is that if f of x is x to the 13, f prime of x is 13x to the 12. So this is the power rule for x equals 13. So the last thing we need to do is just think, well, what about a slightly more general thing? What if instead of 13 I had n? Well, then instead of 13 of these blue x plus h's, I'll have n of them. And this 13 would turn into n. Why? Because I would have n, if there are n terms, I would have n different choices for the lone h in this term. So the moral of the story is that if we have f of x equals x to the n, f prime of x equals n x to the n minus 1. So that's the power rule. This isn't a formal proof or derivation by any means. It's not airtight mathematical logic, but I hope it at least makes it seem a little bit less mysterious. There are a lot of books. Most calculus books will have formal proofs of this. I'm sure Khan Academy has it. There are lots of places you could go. I'm not sure that the formal proof gives that much intuition or understanding. I'm not sure if this gives some intuition or understanding, but I feel it's better than maybe doing a really formal, rigorous proof. Thinking about foiling here sort of being the key step. In any event, this is one argument for why the power rule for derivatives of power functions has to be true. And there's no need to think about this when you're using the power rule. You'll just want to chug through it. It's a nice, simple rule. But I hope it's nice to know that it's not completely mysterious where it comes from.